Okay, today we'll have a presentation by group, okay, on the project. So at first you have to identify the problem and take a case study, and you have to use the advanced analytical model. So try to get the data sets and provide detailed solution using deep learning techniques in artificial neural network. Okay, and then you have to provide step by step on how data be analyzed with deep learning, right? You can use this guide as a cross-industry standard process for data mining, where you can use for your project, alright? And today we will have a project presentation with the project leader and group members. Okay, thank you.
Good day and Assalamualaikum. I'm Siti Nurjihan binti Jari and I will start the presentation by introducing our project on traffic sign recognition system using deep learning. So basically this project focuses on traffic sign recognition using a deep learning approach, specifically convolutional neural network CNN. So we use the German traffic sign recognition benchmark that contain over 50,000 label images across 43 different traffic sign classes. So we aim to build a model that could accurately classify traffic sign under different conditions such as lighting, angles, and background. This demonstrates the potential of deep learning in real-world image classification tasks critical for autonomous driving system. As we all know, autonomous vehicles rely heavily on real-time traffic sign recognition to navigate safely on follow road regulation. So that's why in this project we explore how CNN can be used to solve this problem. Because CNN is one of the most powerful tools for image recognition because they learn spatial features directly from pixel data. So by training a CNN on the GTSRB dataset, we aim to create a reliable model capable of recognizing multiple traffic sign types in various real-world scenarios.
Hi, I'm Desitra and I'll be explaining about the deep learning using Python. So for our project, we use TensorFlow and class libraries. So this will be the import libraries for image, models, layers, metrics, and also the callbacks. And these are the explanation for each import libraries. And this will be the code snippet that we use for our deep learning that shows all relevant explanation with the codes. And this will be our deep learning code explanation using convolutional neural network that is CNN using during our training. So the Python code defines a sequential CNN model where the con2D layers extract the features and shape. And the max pooling 2D is used to reduce partial dimensions in the dense layer to perform decision making. The model has been compiled using Adam optimizer and categorical cost entropy loss function. And for the details, we use convolutional layer 1 and max pooling layer 1. These are the code snippets. So for convolutional layer 1 is applied with 32 filters of size 3 times 3 of the input image to extract low-level features, and the activation function uses value. The code snippet shows the maximum layer 1 that reduces the map feature size by selecting the maximum value from each 2 times 2 block. And this is for convolutional layer 2 and maximum layer 2. Maximum layer 2 works the same as maximum layer 1. And for convolutional layer 2, it adds a deeper feature extraction to help detect more complex patterns that apply 64 filters of size 3 times 3 of the input image. And this is for convolutional layer 3. It adds a deeper feature compared to convolutional layer 2 that applies 128 filters of size 3 times 3 of the input image. And max pooling layer 3 works the same as max pooling layer 1 and layer 2. And this is the flattened layer, drop-off layer, dense layer, and out layer code snippet. So for flattened layer, it converts 2D feature maps into a 1D vector because the dense layer can only accept 1D inputs. And for a dense layer with fully connected layers to learn the combinations of the features of classification with 128 neurons. For dropout layer, it only has 0.5 dropout, which means that 50% of neurons are randomly turned off in the training. And so output layer produces the final classification output.
Assalamualaikum warahmatullahi wabarakatuh. My name is Filza Shazalina binti Masupian. I'm going to present about the flowchart and the step-by-step analysis. So for the flowchart, overall process is starting from the extract alpha, split data for training, validation, and test, pre-process the data, pre-process the image, build CNN model, train model, evaluate CNN model, protein accuracy, visualize using confusion matrix, and then check if the performance of the model is good or not. If no, then we fine-tune parameters and go back to the train model. And if yes, we save the model and do a simulation. So let's go more details in the step-by-step analysis. First of all, for the step 1, a target folder will be created, and finally list all the folders inside the train set to verify that the class label directories has been extracted correctly or not and ready for use in training or further analysis. So next part, a new base split folder will be defined and any existing folder before are deleted to avoid mixing the old data and the new data. Next, new folder are created to store the split data, which is 70% for the training data and the remaining 30% will be split equally for validation and the testing. Then the code loops through each class folder inside the trend set by listing images, shuffling them randomly, and dividing them according to their defined ratios. So lastly, it will print out the class folder in each split to verify that the data has been correctly organized or not. And then the image are resized to 64 times 64 pixels to avoid losing many details and maintain the sufficient details only while reducing the computational load. Next, batch size is set to the 32 because larger batch size has possibility for power generalization even though speed up the training. Meanwhile, small batch will tend to be slow training but better in generalization and improve the accuracy. And then the image pixel values also has been rescaled from 0255 to binary number 01 to normalize the data. Then training image are shuffle the order of the image randomly at every epoch to prevent the model from memorizing the order. However, validation and test dataset are not shuffled. The order as the image may be important for a consistent evaluation. And the next step is build an M model. For this step, firstly, extract features from the input image. For example, first convolutional layer will use 32 filters of 3x3 size where it extract low level features only such as edges and colors, and the second layer will using 64 filters, and the third layer will using 1 to 8 filters. So the max pooling will downsample the feature map by reducing dimensionality such as width and height while keeping the important features only. This pattern will be repeated with increasing filters to learn more complex and deeper patterns. And then we also use the flatten to convert the 2D features map into the 1D vector, while that's also used as X as a decision making layer. And also the ReLU activation function is used to learn nonlinear decision boundaries. So the final dense layer will make the decision based on the highest probability using the softmax. Then the early stopping is used to stop the training if validation loss does not improve for 3 consecutive epoch by randomly drop 50% of the neurons during training to prevent overfit. Lastly, the test data will evaluate the model's accuracy and ensure it performs very well on unseen data. So the next is plot accuracy. So the accuracy curve will show the correct prediction while the loss will show how far the prediction from the actual values. This graph will determine whether the model requires tuning, additional data, or early stopping. If accuracy is high, but the validation accuracy is low, it may cause the overfit. So the confusion metric is the next step, which is despite using confusion metrics to visualize the truth table and predict the predicted level prediction. It shows how well the model is predicting each class by comparing actual labels with predicted labels from the test data. The model will get the actual data labels from the test data set and display probabilities for each class for every image and convert the probabilities into the final predicted class label by selecting the class with the highest probability. Then it will create the confusion matrix, compare actual versus predicted. Next, they get the actual class name from 0 to 42 and format the confusion matrix into the readable tables. And lastly, Seaborn is used to plot the confusion matrix as a heat map where the diagonal cell will represent the correct prediction. And the last step is simulation. So this part is simulate the real world application by allowing users to upload their own image. It will train the trained model will process the image and predict the sign. Then the predicted result will be displayed as output, which demonstrate how the model can be used in a practical scenario such as traffic sign recognition system. I think that's all from me. Thank you.
Assalamualaikum, my name is Nur Najwa and I'm going to present about this question about raw data. So here, our dataset is German traffic sign recognition benchmark. It contains over 50,000 labeled image of road signs, which have 43 categories. For example, speed limit, stop, yield, no entry. It is a real world condition because it has varying image size, lighting, angles, and colors. Next, the raw data is provided as a compressed file named train.tar. The dataset was uploaded manually, like this code here. As a result, a folder named train set with 43 subdirectories are created, which from 0 to 42. And the data divided into 3, which is training, validation, and testing. And the purpose of it is learn patterns from input images for train model, and apply early stopping for validation, and evaluate performance on unseen data for testing dataset. Next is data analysis with deep learning models and output. So here we have CNN architecture with 3 convolutional layers, max pooling layers, dropout layer with rate of 0.5, dense layer with 128 neurons, and output layer with 43 neurons. And the model compilation and training process, we use Adam optimizer with efficient for deep learning. The loss function use categorical cross entropy, and metric we use the accuracy. For the training strategy, we use early stopping and image data generator. And here is the code for the optimizer that I took earlier. And this is the coding for early stopping callback to stop training if validation loss doesn't improve for 3 consecutive epochs.
Now, I will continue for the result and demo part. First of all, this is the result after we train the CNN. The 858 is the batch, this is the epoch, and this column is the training accuracy, this is the training loss, validation accuracy, and validation loss. As the epoch increase, the accuracy should be increased also. And then for the loss, we'll decrease epoch by epoch because the loss is the opposite of the accuracy. So for the batch size, I'm using 32 as the batch size because it is a common batch size. The common value is 16, 32, 64, and 128. Why I didn't use 16? Because if the batch size is too small, then the training will be too slow. And if I use the big batch size, of course it will faster training, but maybe it will worse on the generalization. After that, the yearly stopping also apply for training. So we can see the maximum epoch actually is 30, but the system or the algorithm stop at the epoch 15 because after 3 consecutive epoch, if the validation loss does not improve significantly, then we will stop. And then this is the result for the accuracy and loss. As I said just now, the loss is the opposite of accuracy. So of course, for the accuracy increase, the model loss will decrease. Other than that, we also output the confusion matrix in the heat map style. For the diagonal line is the data point that correctly predicted. So outside the diagonal line, we can see there are some data point is mispredict. Now I will go through the demonstration. Our project is done in Google Colab because this is a very convenient platform and support Python. Now I will present my code in Jupyter Notebook style because it is easier for me to explain. First, this code is used to upload file. After we upload the tar file, we need to extract the tar file to use. This cell is used for trend, test, and validation split. For the trend ratio, is set to 70%, means 70% of the data will take out to become trend data. And the 15% for validation, and another 15% will be the test. Next, this cell is used to pre-process the image. Before go to training, we will pre-process the image and set the height and width of the image to 64 times 64 pixels. Why I don't use 32 times 32? Because it will lose too many details and the image will become very blurred. Next, we will build the CNN model. The number of class is 43, which reflect to the traffic sign, and the convolution, max pooling, and the dense is the essential things in the CNN model. For the convolution layer, the activation function is used ReLU. For the first dense, we're still using ReLU, but the last dense we're using softmax. Flatten is used to convert the 2D feature output from here into 1D vector because after this, the dense only can accept the 1D vector. For the fourth layer, which is the first dense, is the layer to learn the nonlinear decision boundary. For the second dense, it is used to give the output. So the activation function is softmax, means the output will be the probability. So the class with highest probability will be prompt as the predicted output. Now we're going to train the CNN. Before that, the yearly stopping is applied. Then it is set to if the validation loss does not improve for 3 consecutive epoch, then the training will stop. Next, this is the code used to plot the accuracy graph and also the loss graph. This is the code to build the confusion matrix in heat map style. We will save the model, and before that, we have tried this model to simulate the real-world application. So each class, which in number form is labeled to their action name. So now I will run the simulation, and it will make prediction, pre-process, and this is the final prediction, which is general quotient. This means our model can make accurate prediction. Before end, I would like to have a Q&A question. So my question is, do you think this project can be further developed as the real-world application? If yes, can you give me an example? That's all from me. Thank you.
Last but not least, to wrap things up, this project has shown that CNN are highly effective for traffic sign recognition using the GTSRB dataset. Our model built with convolutional and pooling layers followed by fully connected layers achieved over 95% accuracy on test set and handled challenging visual condition well. For future improvement, we suggest testing with real-time video input or using more advanced architectures like ResNet or MobileNet. Overall, this project highlights how deep learning contributes to safer and more intelligent transportation technologies. And lastly, to answer the question, do you think this project can be further developed as real-world application? Yes, I think this project can definitely be developed into a real-world application. For example, it can be integrated into the Advanced Driver Assistance System ADAS or autonomous vehicle to help detect and respond to traffic sign in real time. And that's all from me. Thank you.